Good evening mga lagan. This will be a short video regarding moving loads. Um, this is in connection with the recently collapsed bridge in Isabela. And then there was a photo like circulating in social media about the like a problem regarding or related to this bridge. Um, so the at first I thought this solution was just was just a joke or something because that's typical Filipino. If, like, we always make fun of any disaster or tragedy. And at first I read all his um solutions regarding this problem. So the problem was originally I hid their account just to you know so he said, or the problem says, situation 69. Um, an arch bridge in Isabela is constructed with reinforced concrete arches and tension rods spaced 10 meters apart horizontally. The tension rod supports the bridge deck, which is made of wide flange steel sections. A truck carrying 100 metric tons of boulders travels across the highway. While distance is 8 meters, um, the distribution of the axle load at the front is 30 tons and then 70 tons at the rear axle. Now, the question is calculate the maximum ordinate of the influence line for the shear at A. Then 2 is determine the maximum shear at A in kilonewton. And then 3 is determine the maximum moment in the span in kilonewton meter. Now, at first, I thought this was just a joke. And then I realized, or I wonder, like, why would you spend all this like all the time trying to type all these calculations in the comment section. And then I even like when I look at the calculation here, his calculation for the maximum moment, he assumed, or the calculation, um this one here, uh so the maximum moment in the span typically occurs at mid span, xl over 2, then 30 meters. Now, if you look at the diagram, so it even a question, it says there are tension rods. This one is spaced at 10 meters. Now, his calculation considers the length of the span of the member to 60 meters, disregarding this anchor rod. Now, this anchor rod serves as intermediate supports and then transfer the loads to the arch. So it is the same as if you have a support at its location, this one, you have supports there. So your span in calculating the moment should not be 60. And then he even said maximum typically occurs at mid-span. Now, mid-span, that is if your load is just a single load. Like assuming for the sake of discussion, your span is 60 meters, simply supported. Now, if it is moving load and then there are at least two axles, then your maximum moment is not at the midspan. So let's solve this. I don't know if he is civil because he's literally saying, like, to all the CE civil engineers there, you can practice this, or you can do like solve this problem as a practice. Baka talon pa kayo, which basically means that maybe the EE or electrical engineers and ME are better than you basically. So I don't know if he is a civil engineering student or civil engineering professional or electrical or ME. That I'm not sure, but let's because if he happens to be a student, I would understand. But if he's a practicing professional and this is how he analyzed the structure, then we have a much bigger problem that what was happened on that bridge that collapsed. Um, I will not comment regarding on the bridge that collapsed because I'm not an expert. I'm like you should not be giving any opinion if there was no forensic investigation done. So once the forensic investigation is completed, then that yeah you can you know um examine the report and then give your opinions. But until then, no one should be giving like blaming somebody who was at fault. So anyway, so regarding the problem, so the first question is calculate the maximum ordinate of the influence line for shear A, for shear at A. Now his calculation, influence line for shear at A to calculate the maximum ordinate says of the influence line for shear at A, we consider the influence line for shear A typically triangular function with a maximum ordinate at 1. So yeah, the maximum ordinate of A at of 1 at A. So basically what he means is, so if this is your bridge, now we will assume that there are no like intermediate supports or the suspended or the tension rods. So for the sake of discussion, we will just follow his assumption that this is a simply supported um, beam. So what will happen is to draw the influence line, you will position a 1 unit load at distance x, and then um, you will find the reaction at, say, if this is A and this is B, you will find the reaction at A or the influence line for shear at A or B, and then you will make a like calculation at for example one unit at a distance x until now for simply supported it's always a triangular section. It's either in that direction for B, and then for A it will be like that. And then since it is simply supported, it is always one. Um, the highest would be like the ordinate, the maximum ordinate at either A and B, because although the like in the loading, although the truck is in the direction going to A, but when you design something like this one, you always analyze the worst case condition, which although if you like for this loading condition, the if you calculate the actual shear at A, it will not be the maximum because the smaller load or axle is at the front. But since designing a structure like this one, you will always assume that the worst case, which is the track would be in the direction going to support A or going to support B. Now, the first answer here is correct. Like the maximum ordinate for shear at A is 1. Now, what catches my attention was his calculation for question number 2 and 3. So the question for number 2 is determine the maximum shear at A in kilonewton. Now his calculation, this one, his answer is 826.67. So I don't know, like this is text string. It could be from I don't know MATLAB or like this text string here. I don't know what kind of software he is using, or maybe I don't know. This is for sure. This is not Excel. I don't know this one, but his share at A is 826.67. So I'm not sure why. He already got the influence line, like maximum ordinate of one for share at A. He's already correct for question number one, but when he calculated for the maximum share at A, his answer is 826.67. Now, using the influence line, which is 1, so if this is your span, and then this is your influence line, this is 1, and then this 0, and then your load basically is right here. Yeah, in order to get the maximum shear, you position the biggest load over the support. So you have your 70 tons or seven. His load calculation is on the rear axle is 70 tons and then equals to 7. Um, this is just a rough conversion. It's not really times 10, but it's a normal practice to just multiply it by 10, but it's actually 9.81, which is the gravitational the what do we call this one? The acceleration due to gravity, um 9.81. So usually for in engineering calculations, we just typically multiply it by 10. So 70 tons means or equal to 700 kilonewton. Now this is 700 kilonewton, and then the other load is at a distance of 8 meters, which is 300 kilonewton. Now he already have this influence line, but I don't know why he got the wrong. I mean, I'm trying to follow his calculation, but I'm having trouble um all the 700 times 60 minus 8 plus times plus or divided by 60 plus 300. Um, even if you just draw the shear and moment, like shear moment diagram, and then calculate the reaction summation of moments at A or B equal to 0. But for example, using the influence line, so this is 1, like this whole like for the influence line, this is 1.0, and then this one y, we have to do a ratio of proportion. So the total span is 60 meters, and then this one is 60 minus 8, so this would be 52. So your y would be y by ratio of proportion. Y is to 52, is equal to 1 over 60. Therefore your y would be 52 over 60, which is how much? 52 divided by 60, 0.8667. So to determine the reaction at A, all you have to do is multiply the load by this ordinate here. Like for 700 is 1, and then for 300 is y. So reaction at A, so reaction at A is equal to 700 times 1 plus 300 times 8667. So that would be 700 times or plus 300 times point 8667, 900. So RA is 960, but um, in his calculation, it is 826.67. Now, if you follow this calculation, no wonder the bridge would collapse. Because if you only design the bridge to support 826 for the shear at A, where your actual shear is should be 960 kilonewton. Now, even if we do the summation of moments, it should arrive at the same answer. So you have, so again, like you will position the load, the biggest axle at support. So this is A, this is B. Now, the maximum reaction at B would still be the same. Shear at B would be the same, equal to RA, because when you design, like I said, if you design a structure like this one, you have to assume the worst case condition, which is if the if the track is in the direction of support A or in the direction of support B. So if this is the so this is 700, and then you have your 300 kilonewton. This is 8. This is 52. Now, using summation of moments at A or B. Now, to get the reaction at A, use some summation of moment at B. So, summation of moments at B is equal to the moment at B, but this is a um, simple support. So, moment at B is 0. So, therefore, RA is equal to 700 times 60 plus 32, or no, 300 times 52, and then divided by 60. So that would be 660 plus 300 times 52 divided by 60. So that is the same, which is 960 kilonewtons. So it's either you use the influence line or the summation of moments. It would still arrive at the same answer, 960. So I don't know. I'm trying to figure it out, like I said, why he has only 826.67. Now, based on his calculation, it's 700 times 60 minus 8. And then this first equation, 700 times 60 minus 8, that is um it is as if your load is not on top of the support. Because the only time you multiply the 60 minus 8 is if the 300 or if the 700 is at this location, and then that's why you multiply the 700 by the moment arm, which is 52, 60 minus 8, and then your 300 calculation is 60 minus 16. So it is right somewhere here. So this is the 700, and then this is the 300, which is 8. That's why I don't know why he positioned the axle 8 meters away from support A. That is not the maximum shear at A. If you calculate the maximum shear, you position your biggest load over the support. Now, it's not always like that. It depends. If it's only two axles, then yeah, for sure, position the biggest load at one of the support. But if these are like say five loads, five series of loads, moving loads, then that's not always the case, especially if your total distance between the front axle and the very rear axle is more than this span, then That's different. But on this one, the spacing between the axle is only 8 meters, then your span is 60 meters, and then there are only two loads. So you all you have to do is position the biggest load over one of the supports, which is A. If you want to get the reaction at A, then or the maximum shear at A, then just position the 700 over support A, and then the remaining load will follow. But I don't know, for some reason he positioned the 700 8 meters away. That's why his calculations say 700 times 60 minus 8, and then plus 300 times 60 minus 16. I just don't know why he positioned it 8 meters away. But yeah, so the maximum shear at A should be 960 kilonewton. Now, on the second question, um, determine the maximum moment in the span. Now, again, this should not be the solution, because these are not basically this bridge is not a simply supported bridge. Um, like, or I would say the deck. The deck is not simply supported because it is technically supported by this tension rod, and transfer that load to the arch, and then the arch would be the one transferring it back to the main support. So his calculation, the maximum moment in the span typically occurs at mid-span, which is not correct. If it's only a single load, for example, this is your beam, and then you only have one moving load, then for sure your maximum moment would be at the mid-span. But if you have two or more than two loads, then you position your biggest the center line of the beam will coincide with the mid distance between the resultant and the biggest load. Now, to solve for the maximum moment, first you have to get the location of the resultant. So this is your load, which is 700, and then we will position. Um, so this one is 300 kilonewton. 300 kilonewton. This is 7 kilonewton, and then this distance is 8. Now, all you have to do, like first, is to get the location of the resultant, which is 1000 kilonewton. Now, by summation of moments, say you want to know the distance, like this one here, from like distance from 700 load, from the 700 axle. So to determine x, you sum up your moment, say from here. So that would be 1000 times x is equal to 300 over 8. So x would be, oh, this is not divided. This is times 8. Oh, not 80 times 8. So 100, so this one, or 1000 times x is equal to 300 times 8. So x is equal to 300 times 8 over 1000, which is 300 times 8 divided by 1000. 2.4. 2.4 meters. So this distance x is 2.4 meters. So this is 2.4. And then this, since the total is 8, so this is 5.6. Right. So 2.4, 5.6. So to determine the maximum moment for moving loads, if you have two moving loads, so this is your span, which is A B, which is 60 meters. So you get B center line. So this is 30 meters. This is 30 meters. Now, for moving loads, it says that to get the maximum moment, position the the center line of the beam between the resultant and the biggest load. So now the distance is 2.4, like this one here. So divide it by 2, so that's 1.2. So therefore, the 700 load is, so at 700, this is 1.2 because the resultant is right here, which is another 1.2. So that, which is 1000. So that is how you position your load to get the maximum moment. So, so this is 700. Now, the other load right here would be the 300, which is 8 minus 1.2. I mean, this distance. So 8 minus 1.2 is 6.8. So that distance from here, from the center line. So that is your position. Now, in his calculation, he just positioned the load, which is, I don't know, for some reason, he, instead of using the actual load, um he used the what we call this one, the shear, and that 806.67 times 60 times or divided by 4, that is the maximum moment of a simply supported beam with concentrated load at the midspan, which is basically like this. If you have load at the midspan, load P, this is L over 2, this is L over 2. Your moment, maximum moment is PL over 4. But that's not the case for this one because we have two loads. And then for two moving loads, you have to position your center line of the beam between the resultant and the biggest load. So that's why if we redraw that one, this will be our um, or yeah, we'll use this diagram. So basically 700 right here is 1.2 from the center line. So if this is 30 minus 1.2, so this is what? 28.8. So the first load is 28.8 meters from the support A. So 28.8 plus 1.2 is 30. Now this one, if you sum up, so this one is 28.8, and then this is 8, so that's 36. So the remaining, so 60 minus 28.8 minus 8. So this one is 23.2 meters. And then this is 8. So we'll just redraw that. So this is your load for the beam A, B, and then your load here is 700. This is 300. This is 8. This is 28.8. And then this is 23.2. So 23.2 plus 28.8, that's 51, uh 52, and then plus 8, 60. So the total is 60. Now, now there are two ways to calculate the maximum moment. It's either you draw the shear and moment diagram. So for example, that's the um, load diagram. So to get the reaction at A, we will have now this reaction at A, this isn't the maximum shear at A. This is the reaction at A that will give the maximum moment. So summation of moments at B, to get the reaction at A, summation of moments at B is equal to 0. So RA is equal to 300 times 23.2 and then plus 700 times 23.2 plus 8 is 31.2 divided by 60. So that is 300 times 23.2 plus 700 times 31.2 divided by 60. This is 480 kilonewton. Now, reaction at B, summation of moments at A is equal to the moment at A, which is 0. Therefore, RB is equal to 700 times 28.8, then plus 300 times 28.8 plus 8 is 36.8. 36.8 divided by 60. So 700 times 28.8 plus 300 times 36.8 divided by 60. This is 520. So to check, RA plus RB should be equal to the resultant, which is 1000 kilonewton. So 480 plus 520 is equal to 1000. Therefore, our reaction is correct. Now, if we draw the shear moment diagram, so this is so you have from here you have the reaction at A, which is 480 going up 480 and then straight because there is no load at this location 28.8. It will go down from 480 minus 700. That would be 480 minus 700. So that's minus. It will go down to minus 220. Then it will go straight again. Then down by minus 500, minus 300. So this is minus 520 straight again. Then reaction at A, which or B, is 520 back to 0. So it should be 0. Now, to get the moment, you will just multiply or get the area of either this one, the top one, or the bottom one. So the top one is your moment is this is straight line, so this will be triangular first degree curve, which is a diagonal. So 480 from here, that is 480 times 28.8. 28.8 is equal to 480 times 28.8. 13824. 13824. And then this one would be minus 220 times the distance 8. So minus 220 times 8 is this is 12064, and then minus 520 times what's the distance? 23.2. 3.2 is 0. So your maximum moment is 13824, right? So max is 13824 kilonewton. Now his calculation He just used PL over 4, and then for some reason he used P equal to the shear at A. So which is, I don't know. I wish or I hope he's just a student. If he's a practicing professional in that size calculation, I don't know. Bridge will certainly collapse if that's the case. So his calculation is, yeah, this one, 12,400. So imagine if you design this one and following this calculation, you have to design your structure for maximum bending of 12,400 kilonewton meter, and then get the section modulus from that, and then you will have the section. Now, instead of 12,400, your bridge section should be designed to a maximum moment of 13,824. So that's way higher than 12,000. So if you design your load or your bridge for 12,400, that will fail because the maximum moment based on that load, moving load diagram is 13824. Now, the other way to calculate for the moment is you just cut section at the maximum load location, which is this one here. So to do that one, you just draw the free body diagram for that section. So this is your segment, right? So this is what, 28.8. So this is 28.8. And then this is your RA, which is how much? 480. 480. And then this is your location of your 700 diagram, 700 kilonewton load. And then you have your shear at, say, X, and then your um, moment at X. Now, to get the moment here, summation of moments at X, this is distance X. So moment at X is equal to 480, 480 times 28.8, which is the same, 13,824, right? 480 times 28.8. Yeah, 1324. So on the other side, the same. So we just have, so draw the free body diagram to the right of 700 kilonewton location. That would be the remaining, which is, what's the distance? Um, 23.2 plus 8 is 31.2. So this is 31.2 meters. And then this is your reaction at B, which is 520. And then you have your load here, which is, this is 8 meters, right? So, yeah, 8. So this is 23.2, this is 300. So this is your moment at X. This is your shear at, or going down. This is your shear at X. Because we already have here at the top going up. So this one would be going down. And then this one is counterclockwise. Now this would be clockwise. So mx is equal to 520 times 31.2 minus, this time we will subtract 300 because it's in the same direction as the mx clockwise. So 300 times 8. So this one, 520 times 31.2 minus 300 times 8. So 13824 kilonewton, which is the same as if you calculate the, or if you use the free body diagram for on the left of the 700 or the right, so that should be the same. Or if you do the shear and moment diagram. So to summarize, for number two, your shear would be 960 kilonewton, and then three would be 13824. This is kilonewton meter versus in his calculation, this is 800, 826.67, 826.67, and then this one is 12,400 kilonewton meter. So imagine the difference. No wonder the bridge would fail. So yeah, that's why if like I myself I don't offer opinion on what happened on that bridge because I have a limited knowledge on bridge design. I know, I mean, this one moving load. This is just theory of structures, So this is just analysis. So I know how to analyze that one, but the design itself, I'm not really. I mean, I've designed like bridges before, but not for highway bridges, but for the forestry services, and it's different loading, and it's most of the like 99% of the time it's simply supported, so it's really not that complicated. But on this particular bridge, we have the tension rod or the this one suspension rod. Then that would be considered as a like an intermediate support. So it's the bridge itself is not really simply supported, but a or the deck, like the bridge deck is not designed as simply supported, but a continuous span. And this one, what I'm showing is I'm just following his assumption that the brace is simply supported. And then I told him like, I asked him like, why is your maximum moment at 30 kilonewton or at 30 meters or at mid span? And then his response was, because it is simply supported, the moment is always at the midspan, but that's not the case. If it's just a single load, then yeah, sure. Like I said, if this is just a single load, this single load P, then of course your maximum movement will be at the midspan. But if you have um two moving loads, then that's different situation. You have to like the you have to like to determine the maximum movement. You have to position the center line of the what we call this one center line of the resultant and the biggest load to the center line of the beam. Um, that's just how the moving loads are analyzed. Even if we do a um, like a check, for example, what if we position the biggest load at the center? So what will happen now is if this is your so what will happen now is um, what will happen is, say, for example, this is your bridge girder. So if you position the biggest load at the midspan, so this one I will just prove to you that um, what we calculated earlier was the maximum moment, where you position the the half of this resultant and the biggest load over this or align it with the center line of the beam. But for the sake of just to check, this is 700, so this is 30, and this is 30 meters, and this is 30 meters. And then it's either way, either left or right. So say we'll position the 300 here. This is 8 meters. So therefore, this is 22 meters. So this is A, this is B. Now, to get the reaction at say we'll just use, or we'll just get the reaction at A and then multiply it by 30, then that's the moment at this point. So we'll just get the reaction at A. So RA is equal to 300 times 22 plus 700 times 30 divided by 60. So 300 times 22 plus 700 times 30 is equal to, divided by 60, 460. 460 kilonewton. Now, moment at this, say, distance or a point x, at midspan, moment at x is equal to RA, which is 460 times 30. So that, like, if you draw the shear moment diagram, so this would be for 160 and then straight then down. So this would be your area. Multiply that to get that area, that's your moment. So basically 460 times 30 is 13,800. 13,800. Now, how much did we get? 13,800. So, how much did we get? Moment is 13,824. See? So, if you position the load at the center, it will only give 13,800 kilonewton meter, which is still less than this one. So even if you try, like, say, position the biggest load like 29 meters, or uh zero point 0.5 meters from the center line, it will give a value less than this one here. So I hope this is clear. Yeah, this problem has been circulating, and I was just like, like I said, this calculation caught my attention, and yeah. So anyway, I think that's it for now.